Welcome to this video on the topic of vectors. In this lesson, we're going to learn about position vectors. Position vectors may be used to describe how to move between 2 points in space. Consider we have points A, B, C, and D, and these 4 points form a parallelogram. So if I were to connect up A to B, B to C, C to D, and D to A, what we'd get is a parallelogram. Now remember, position vectors describe the movement between 2 positions in space. So if I wanted to move from A to B, I could describe the movement from point A to point B using the position vector AB. I can show that it's a position vector by simply changing the side of this parallelogram into an arrow, and I'll simply name it AB. So AB shows me how I move from point A to B. Similarly, for B to C, I can simply redraw this side as a vector, and I'll name it B to C. Notice that I'm choosing to draw the arrow from B to C, and likewise I say I'm starting at B and finishing at C, so I call the vector BC. So my start, my end. Furthermore, from C to D, draw the arrow, I'll call it C to D. And finishing up, I'll say D to A, it's just vector DA. Alright, these are our position vectors here. We remember that a position vector shows us how to move between 2 points within space. Let's have a look at how we can describe these quantitatively. Below I have 5 examples, A all the way to E. These are all going to increase in complexity. Now, OA, we want to describe the position vector OA. We don't have position O listed on our diagram here, but reading the initial text, we can see that point O refers to the origin. Now this one we're going to take a leap of faith, and I'm just going to tell you what the answer is. To describe position vector OA, or the movement from the origin to point A in space, all you need to do is grab the coordinates of point A, which is 1 and minus 4, and we write it as a column vector. Similarly for OB, the movement from the origin to point B in space, we simply grab the coordinates of point B and we write it as a column vector, 4 minus 1. And life is good. Moving along, let's increase the complexity. We're looking at the position vector AB. Now before we can describe AB, what we need to do is we need to go back and we need to understand why is OA simply the coordinates of point A and OB simply the coordinates of B. So if we concern ourselves with position of the origin, we can simply say that the origin lies here. I know it doesn't, but it's just for representation purposes. Next, what we might choose to do is choose to draw in the position vector OA. Now the position vector OA is going to start at the origin over here, and it's going to go to point A in space over here. So drawing this in, my position vector looks like that, and this is position vector OA. For B, it looks like this. Now, moving back to position vector AB, how do we describe the movement from point A to point B? Well, we have to look at our diagram, and we know that to go from A to B, we're going to start at point A and finish at point B. But we don't have values to describe how to go directly there. So rather than going from point A directly to B, what we can choose to do is we can go from point A and move back to the origin, and then from the origin, move across to point B. The reason why we do this is we know that point A, to get there, we simply go along the vector OA, which is 1 minus 4. To get to B, we simply go along the vector 4 minus 1, like shown over here. So what we might do is we'll go from A to B by choosing to go from A back to the origin, so this guy here, and then from the origin across to B, so this guy over here. Now when we're traveling from A to the origin, we're going against the direction of the vector, So we're going in the opposite direction to OA. So OA is going to be negative. So writing this out, to get to AB, we're firstly going to go in the opposite direction of OA, and then we're going to go in the direction of OB. And this is our expression here. So you subtract the starting vector from the destination. And this is the rule we employ to be able to find position vectors connecting two non-zero coordinates within space. Alright, putting the values in. OB, we know it's going to be 4 minus 1. OA is 1 and minus 4. I simply compute this using my knowledge from the previous learning. And I know 4 take 1 is 3, minus 1 take negative 4 is 3. So the position vector that describes how to get to AB is just 3 and 3. So the calculation is quite straightforward, even if the instruction is quite complicated. Okay, next level of complexity, C to D. We want to describe how we move from point C across to point D over here. Now if we look at this, we don't know the value of point C in space, but we need to look at the context of the question. This diagram over here represents a parallelogram. In other words, this side over here is not just the same length as this side over here, but they're also parallel, as in they're pointing in the same direction. Remember, vectors have direction and length. The direction is the same between these sides. The length is the same between these sides. And because of that, what we're going to find is that AB is very similar to CD. So we can say that CD equals AB. But there's a catch. Notice the direction of the vectors here. AB is pointing in an upwardly direction. CD is pointing in a downwardly direction. The directions of these vectors are opposite one another. So CD doesn't equal AB, rather CD equals negative AB. And because CD equals negative AB, we can simply say that negative 3 and negative 3. So this is the relationship here. We're able to know what CD is because it has the same length and an opposite direction to AB. So we can simply get AB and make it negative, and there's CD. Remember, this works because it's a parallelogram. BC is going to be equal to negative DA because they have the same length, but they point in opposite directions. Now, this leads us into the final question. We want to determine the location of point C. Looking at this, we know that point C is up here. There's no coordinates listed. However, there's a relationship between CD and AB. The relationship is that CD is equal to negative AB. Now, if we say that CD equals negative AB, just like so, what we can do is we can break this up into its smaller components. CD equals OD, take OC. AB is the same as saying negative OB, take away OA. So what we're doing is we're doing a bit of algebra here. Next, we want to know what the position vector of how to go from the origin to point C. So what I can do is I can subtract OD from both sides. This will give me negative OC. And then finally, I'll multiply both sides by a negative 1. So OC is equal to OB take OA plus OD. Now all we need to do is simply sub in the position vectors for point B, point A, and point D, compute, and that will give us a position vector for C. From there we can convert it back into its coordinate. So OB is 4 minus 1, is 1 and minus 4. OD, 7 and negative 3. This gives us the expression 4 take 1 plus 7, and then minus 1 plus 4 take 3. The top line is going to give us 10. The bottom line is going to give us 0. So what we discover is that the way in which we get from the origin to point C is using the direction vector 10, 0. So therefore, what we discover is that point C is going to be at 10, 0. If we look at our diagram above, if we throw in 10, 0, then it clearly seems to look the part. So you go from here, it's minus 4 to minus 1, minus 3 to 0, 1 to 7, 4 to 10. So the way in which we can calculate unknown points in space is by the careful manipulation of position vectors. So we can break them apart. We can say that they're the same as over here. It allows us a tool to be able to describe geometry without not necessarily knowing its original position here. So this question here demonstrates how we can find unknown positions in space by using position vectors and using known relationships from before. So in summary, what we learnt about in this lesson was, what are position vectors? We learned how to describe position vectors numerically. We then learned how to determine position vectors that weren't just pointing from the origin to a point in space, but rather pointing between two locations in space. We learned how we can use known relationships to discover unknown quantities, and then we learned how to find points in space that were unknown using position vectors.